Hello everyone, good afternoon. My name is Gnani Dattatreya. I work for Capital One, and Capital One also has a booth in the Conference Expo. Please stop by to find out what are the awesome things that we work in Capital One. It's a pleasure for us sharing our experience in containers operations management and automation with you today. And here is my colleague Satya.
Hi, thanks everyone. My name is Satya Shanmugasundaram. I'm also an enterprise architect at Capital One. This is what we are going to expect from the session today. We are going to review how Capital One embraced microservices and Docker, and how ECS has simplified our journey, and how our container stack evolution happened. Starting with classic ELB and with the availability of application load balancers, the infrastructure stack evolved quite a bit to solve specific problems. So we will review our different infrastructure configurations. Then we will look at different operations, like how we create the infrastructure stack and manage it, doing AMI updates, different deployment models like blue, green, and canary deployment automations. Then we will review some of the lessons we have learned by the adoption of ECS and Docker, and what are we going to look forward to.
All right, so it's an exciting time for us in the Capital One Technology Organization. We are utilizing cloud first, open source, and microservices architecture principles in building world-class digital products. Speaking of microservices, there are two aspects to this. One side of the coin is the domain aspect of it, where our domain experts work on the scope, size, API, and ontology of our microservices. On the other side of the microservices coin is the DevOps side of the things, where we focus on independent runtime for our microservices, independent deployment, and scalability. And this is where we use Docker to run our microservices as containers in AWS Cloud. So in embracing microservices architecture for running our apps in AWS Cloud, we embraced Docker and ECS, Amazon's EC2 container service. And our journey evolved over a period of last 18 months in using these two solutions, using these two products. Right, and ours, Capital One, is a federated operating model. It's a large enterprise, and ours is a federated operating model. And what it implies is each team builds and owns their application. So you build, there is no central team where all of the enterprise goes and deploys their apps as containers. Each application team has the autonomy, and they have they can deliver at their own speed, independent of other teams in running their apps. Right? So running Docker containers by itself is not very helpful for delivering microservices for large enterprises. It is the DevOps pipeline, along with the container management solution with the enterprise capabilities and operational aspects with production ordered things, that is what makes the microservices click for the large enterprise like ours. And so we have tens and hundreds of teams, and all of them have their individual stacks to run their microservices, which means there will be tens and hundreds of creative solutions if all of them start writing their own infrastructure code to run their, to create their stack in the cloud. So we created a set of self-service automation tools to provide that reliability and scalability for our application teams to run their microservices. So as an application owner, I am focusing only on my application development and not write a single line of infrastructure code to run my Docker apps as microservices in the cloud. So rather, as an application owner, I would have my app, build the Docker image, and then provide a set of properties file, and you provide that to self-service automation tools, which will create the stack and run your services in cloud. And we have these tools covering different operational aspects of it, which we will do a deeper dive today. Right? So we started Docker journey, like way before ECS was available to use in private VPCs. So we had open source solutions for container management solution. And since then, we understand it is not trivial to run container management solution with number of components that are required to provide dynamic service discovery, load balancing, operational aspects of it. So we started embracing ECS, and today ECS is the most adopted container management solution in the company, right? So we run different types of applications. So from the business side, it's the credit card servicing application, auto loan servicing application, enterprise applications. All of them take advantage of Amazon's ECS and Docker solution. We run different types of architecture applications. We have run microservices, event-driven applications, batch applications, real-time APIs, and all of them use ECS-based solution. And ECS significantly simplified our container solution, which we will see in the due course of this presentation. Right. One of the things that is very exciting for us for using ECS compared to open source solution like Mesos, which we used in the beginning, is ECS deeper integration with AWS native services. Like we take advantage of IAM roles, the auto scaling, the CloudWatch metrics, and how we monitor all of the AWS deeper integration with ECS. We take advantage of them, right? So with ECS and our automation tooling, we have significantly reduced the time required for the application teams to run their apps in AWS cloud with fully hardened production-ready container stack. So moving on, I talked a little bit about the container management solution that is required to run your containers, not just running containers, but what are all the other things that goes with it, right? So this is the end-to-end pipeline view of our DevOps pipeline for our for delivering microservices, right? And here, so I want to talk about a little bit about each component in this pipeline. And our goal is build an operationally simple solution for each of the component. We don't focus too much on what tool sets we use because tools will change, and we want to build each component in the pipeline with an operationally simple solution, and then we want to integrate all this with the APIs. And tomorrow there will be a better tool that solves for the same component capability, then we will have to swap that one out. And we did this swap out some of the tools, what you see here, right? So this is developers on one side, on the other side is your end users who are your app consumers, right? And we have source control management, and we use GitHub Enterprise, and we use for build we use Jenkins. We have two types of repos. One is the code binary repo, and the other one is the Docker image repo. We use Nexus and we use Docker registry, right? And this is the runtime piece of your container management solution. This is where your microservices run as containers. And what are the components or the capabilities, right? We need a compute cluster. We need a cluster manager. We need a container scheduler, right? And those are the components, and what is the solutions we use. EC2 instance for the compute cluster, and for cluster manager and scheduler, we use ECS, right? And service discovery, and dynamic service discovery and load balancing. And before application load balancer was released, we ran our open source based solution for dynamic service discovery and load balancer, right? So dynamic service discovery, we used a console, and for load balancing, we used Nginx. On the later version of our stack, which we will see, we use AppELB to provide the same functionality, which is the dynamic service discovery and load balancer, right? And we have the ELB, and that is front-ended by API gateway, and this is our clients access their apps. So the pipeline view, the DevOps pipeline, how it works. Our developers check the code into source control, and the tech lead commits the code and accepts it. It triggers the build, and the build would be like compiling the code. If it's the Java-based application, pushes the code to our binary repo on the Jenkins server also builds the Docker image, pushes it to a Docker registry, and makes an API call to our cluster manager, and that will deploy our service in this container management solution. And depending upon what stack we use, the containers that run gets registered into the service discovery solution, and it will be available for use via the ELB endpoint to our API gateway. And API gateway handles all the gateway specific capabilities. So this is the end-to-end pipeline view. The operations tools and the operations automation tools, which we will go into a deeper dive today, is these dotted parts. So all these pieces are like enterprise standard things. Each application team doesn't have to run or own those things. It's a standard enterprise shared services. This is what each application teams create to run the runtime for the microservices. They provide the input to our automation tools. Our automation tools stand up and run them, right? So which we'll see them. So moving on to container stack evaluation.
Looking at container stack evaluation, this is about creating our infrastructure stack. The infrastructure stack highly depends on how we load balance Docker containers. So one of the significant problem statements in running Docker containers in production in a very high availability mode is, how do you do service discovery? How do you do load balancing? We all know that Docker containers are launched at high ports, something like 32,000, and they can come and go. You cannot count on Docker containers running forever. So sometimes they come very ephemerally, like few minutes you can launch and do something. So how do you load balance these things? How do you discover these things? How do you register these things? This significantly depends on what tools we use and what the tool provides and what are those missing pieces we got to glue it together. So we will go through from classic ELB all the way up to application load balancer, which was just released in August. In the solution number 1, when we started, we had ECS and classic load balancer. This is a very simple stack. When you launch a Docker container, it will launch it into your compute nodes. The ECS agent will register the instances to the classic ELB, and stack is very simple. And if you want mutual SSL authentication, you can decide to do TCP load balancing, and your containers can do the certificate verification and all that stuff. We will go deep dive into the solution after we review all the available solutions. Okay, what if you want to do more density packing, and also we want mutual SSL authentication? Density packing means now you want to be able to maximize your compute cluster. If you have a M4 large instance, you want to take advantage of all the CPU and memory. In this, we use ECS with classic load balancer, with console and registrator doing the service registration part, and Nginx along with the console template doing the load balancing part, and this provides you high density packing. Then in August, during the New York Summit, AWS made general availability of application load balancers, which provide the service registration and discovery part. So in the solution number 2, we don't need those on the right side. So this provides a simple stack. It's a high density packing, but we do not have support for mutual SSL, so which we'll go through why. This is the first solution, ECS and classic load balancer. So in this, the key thing to note is you need to have a fixed port configuration mapped for the Docker container to host port. Let's say you are running Apache and you are running it on port 8080. You need to have port 8080 or any other port mapped to the host. What that means is you can only run one container of each service in the same EC2 instance. So that kind of limits you. If you have a 3-node cluster, you can run the service only in only three containers you can launch because of the fixed host port. So that doesn't mean that this limits you to a large extent. Say if you have a large compute cluster, you have a large number of services, and if you can manage the port configuration yourself and count on ECS to manage all of that, and you need mutual SSL done at the container level, this will still work great. So this is still used by some teams for the simplicity of the stack. Now let's look at, I want density packing. I want a couple of services running in 10 servers. I want, say, 200 tasks to be run, and I want complete service discovery management. So in this case, what happens is we run a highly available console cluster. Looking at here, this 3-node console cluster interacts with this compute cluster. We have console agents deployed in the compute cluster. We have a component called registrator, which is an open source software, which listens to these events of Docker containers as launching. Doesn't matter what port Docker container gets launched. So that gets registered into the console central agent through to the console servers. Everybody polls the console servers through something called console template. And the console template, it's like event driven. Every time the console server reports a change, it updates the Nginx templates. It almost updates real time. And the Nginx templates reloads the most recent update to the load balancing endpoints. And the classic load balancer still routes a TCP load balancing to the Nginx layer. So you have one Nginx process running in each of these EC2 instances, and the Nginx will route it to any of these instances. There is no guarantee that this Nginx will only route to this, because there is no affinity here. We tested that it is less than 1 millisecond latency, even if you were to go to a different instance. In this case, this is an auto-scaling group with highly available configuration. This is an auto-scaling group. This solves the high density packing issue. So you can run hundreds or thousands of containers, and this console cluster will manage it. And you can still do mutual SSL authentication. You can do TCP load balancing here, and Nginx can do mutual SSL and certificate verification, and can still pass those details to the containers. The containers can further authenticate the Nginx as the source and do any other header validation, like the name of the original certificate that was passed. So this provides you, in spite of the complexity, this has been still very popular within our solutions, because it solves most of the service discovery problems, and it still supports mutual SSL authentication. Then came application load balancer. Suddenly, the stack is significantly simplified. There is no console or Nginx processes to manage. Now, if you look at here, if you're not familiar with the application load balancer, it is like classic ELB, like entry point, but you cannot load balance TCP here. You can only load balance HTTP or HTTPS, and that uses something called a target group for all practical purposes. Target groups are like your load balancer. The target groups works with the ECS agents in each of these ECS instances, and the ECS agent, as soon as the services come and go, they register with the target group, and the target group gets load balanced by your load balancer using the context paths. So you can run multiple containers, multiple services, any number of containers in this simplified stack. And one of the key limitation is you can only do a HTTP or a HTTPS load balancing here. So that means once you terminate the SSL, your originating client certificate information cannot be passed back to the containers. So you have to rely on perimeter security, like security groups, network access control list, to manage the security. So, but this provides a significantly simplified stack for the specific problems we are interested in.
All right. So you saw three different types of stacks here, right? So for the operations automation, what do you want to do, right? So for us, operations automation is the force multiplier. And like I said earlier, our application teams, we want us to focus on the application development and not each of the application team run or the right infrastructure coding for running the microservice stack, right? So we created the self-service automation tools that does 4 things, or like it does fall under 4 categories. One is the tools for stack creation, and the tools for deploying your microservices using different release strategies, blue, green, or canary. And we have tools for army updates, right? So we manage our own armies, and we want to rehydrate our stack with the latest armies and the tools for that. And we have tools for scaling and monitoring. So these are the 4 buckets of tools that we develop, right? And how our users use these tools. Our users prepare a property file describing where they want to run their application. It basically contains information like what is the AWS account and what is the subnets, availability zones, etc. To create their stack and provide that tooling to either a Jenkins job or to a Lambda function. And this Lambda function or Jenkins job will create the stack for them, right? And likewise, we have tools for blue-green and canary deployment. These are all like Lambda functions, and our folks trigger these Lambda functions by dropping a parameter file to a bucket, and this will provide them those tools. And the Army update automation tool, likewise, they say this is my older Army that is using my stack, this is the newer Army, and we have the tools that rehydrates the stack with the latest Army, and there is no user disruption, end user disruption. It copies over all the services from old cluster to new cluster. That is another tool. And we have tools for health checks at the container level, at the instance level, and at the auto-scaling group level, and at the cluster level, right? And we have integration of our stack with the enterprise logging system. We use Splunk, and as part of the tooling, we have the Splunk agents that is bootstrapped and connects to the Splunk server and all that good stuff, right? And we also have built a test apparatus, which is a standalone machine where we have JMeter, InfluxDB, and Grafana, and a number of JMX templates. So the application teams, when they stand up this stack and they deploy their services, they also have this test apparatus launching tests on their services for the different types of JMX plans. Like, you may have like a constant throughput, or you may have like a step-up throughputs, whatnot. They have that tooling also in their hands. So, and let's go over these 4 categories of our automation tools and have a little deeper dive into these tools.
In this section, we cover the infrastructure creation automation. Why do you have to create the infrastructure consistently? As Nadi said, we have several agents, the company-specific security agents, SSH agents, monitoring agents, some file system standards, all that stuff we have to create in a consistent manner, writing each developer having its own CloudFormation template or Terraform is going to create a sprawl of these templates. So this is how our infrastructure stack creation process looks like. So as an application owner, the developers are expected to prepare a property file. So all they have to know about is which VPC. They are already in an account, LOB specific account. They have VPCs, subnets, security groups, what instance size you need, what is your auto-scaling group size. If you are using your auto-scaling policy, what are your metrics for CPU, memory, disk, all that stuff. And provide some SNS topics for critical alerts, normal alerts, all that stuff. Then they create these parameter files, and each LOB is designated with a specific S3 bucket, and that triggers a Lambda function. The Lambda function executes a Terraform template, and the Terraform template creates the infrastructure. It takes about 3 minutes once you drop the bucket for the ECS agent to register into the server and ready to launch containers. So why we choose Terraform? That is, you can go both ways against CloudFormation template. We have some modularity and more readability, and developers can also do quick desktop testing and all that stuff. So we prefer Terraform. So we ran Terraform originally in the Jenkins with the Lambdas, with VPC support and all that stuff. We started running Terraform within Lambda. It still finishes within 5 minutes, so we haven't hit that limit yet. So this is how a typical parameter file looks like. My instance type is M3 medium. These are my subnet 1, 2. You can provide any number of comma-separated subnets. My comma-separated security groups, my ASG min is 3, max 9, and all that stuff related to the compute cluster. Then my ECS cluster, this is my name. It will create an ECS cluster. This is my IAM role for my cluster because it needs to access S3 buckets and whatnot. This is our internal Docker registry URL, and we have a proxy server, so we need to have that. Then this one section covers all the alarms and scaling policies. So all the scaling policies, say if your CPU is more than 80 and scale out This is more reservation policies for ECS. We also have utilization policies. So it's all abstracted into parameter files. The templates create those CloudWatch alarms and manage the ECS, work with the ECS clusters for the scaling policies. Then some teams may want to have a custom script because they have a specific log file configuration, or they want to download a certificate from their S3 bucket and configure the containers with the host volume mapping and use something with that. So we provided a custom script. Anything we didn't abstract in our main stack, people fill this with this gap, and they do all kinds of stuff, whatever the custom things needed for the application. So this is how a 3-stage stack creation happens. We separated the 3 stages because the compute clusters typically, each time AMI changes, we have to, it can be 1 month or 2 months, or as often as you want. Something changes, your security group changes, all that stuff. You can, if you want, you can recreate the cluster as many times as you want. So we create the compute cluster in one set of parameter files, create the compute cluster. It's a different folder on the same S3 bucket, so it gets triggered according to which event gets kicked off. Then we create a load balancer with a default target group. In this case, this talks about application load balancer stack. And in this case, the load balancer used to outlive the compute cluster, so it can run for months or even years, because the DNS name, people don't want to change it, all that stuff. So basically, we create a load balancer, and we attach the load balancer. We register these auto-scaling groups along with the third stage, in this case here. The third stage is services. This is a one-to-many. This you can, each time you run it, you create a service or an update a service. So you run it as many times as you want as the number of your services. So this has things like what is your container image, what is the number of tasks you want to run, and what is your deployment plan, minimum deployment 50%, maximum 200, and all that stuff. All ECS service related stuff gets abstracted into these parameter files, and once they do this, the stacks, these services get, each service get its own target group, and the target group registers with this load balancer with a context route, and you can start getting load balanced. Typically, if you have your parameter files, first time it may take an hour for an application team to work with their security team and other administrative team to find their right subnet security groups. Once that homework is done, probably 1 or 2 hour maximum. The total time it takes, if you have a Docker image to run, it takes about 5 to 7 minutes to run end to end. And if you no longer want it, you can destroy it in a few minutes. So, and you can do it as many times as you want. So it's a you build, you own. So developers create this hundreds of times a week and destroy it as often as they want.
All right. So what we just saw was like as an application team, I used 3 micro functions, and I created my stack that runs our microservices, right? So, and we use Capital One private Amazon machine images, and our cloud engineering team releases updates to our armies periodically. And as our security and regulatory requirements mandates us, we are required to rehydrate our EC2 machines with the latest armies. And when we have a stack that we have microservices running them, how do we update our application stack with the latest armies without causing any disruption to our end users? That is this set of army update automation tool, how that works. So here is the example where I have an application, right? And I have this ECS cluster. This is my application load balancer. And in this application, I have 2 services. Each service running 3 tasks here, 1, 2, 3. So there are 2 services, each service running 3 tasks, and I have 2 EC2 instances. And as we can see, this is old armies. I'm getting notified by my security team that I need to rehydrate my stack with the latest armies that has been published. right? As an application team, I don't want to write infrastructure code to update my armies, but I don't want to cause any disruption to my end users who are using this load balancer URL that are accessing my services. And I want to do this in less than a half hour, and I want to use the automation tools to get this rehydration done. And here is how we do that. So again, most of our automation tooling is event-driven via Lambda functions. And what, as an application developer, I do, I prepare my properties file, and I drop it in a S3 bucket saying, this is my stack, this is my old army, and this is my new army, and update my stack, right? So I drop that function, I drop the parameter file, it kicks off this Lambda function. This Lambda function is going to go and create a brand new ECS cluster, and it's going to create the same number of, in original stack I had 2 machines, it's going to create same number of machines, but this time with the newer armies. This is my first Lambda function. And I have my next Lambda function, which gets triggered, and this is going to go and replicate all my ECS services that is running in my old army-based cluster to my new army-based cluster. So what's happening here is when these 2 ECS services are created in this new ECS cluster, these services are also getting registered to the same load balancer, to the same app load balancer target groups. So at this point in time, what do we have is, we have this application load balancer, and we have, at this moment, doubled the capacity of our services. One set of services running in the new army-based ECS cluster, the other one is running on the older army-based cluster, right? So now we have all of these things perfectly running. Then we have the next Lambda function that goes and deletes my ECS services. It first gracefully stops the ECS services, meaning all the containers get stopped on the old machine, and the draining happens so we don't break any in-flight transactions. And once all the containers are drained in the old stack, you have the ECS services stopped, and then it will delete the stack. It will remove, it will terminate the EC2 instances, it will terminate the launch configuration, auto-scaling group on the ECS cluster. And what do we have now? We have the new AMI stack running the same ECS services, same number, but with this new AMI, right? So in less than half hour or so, those 3 micro functions work together in rehydrating your application that was using your old army with your new army. So that is how we do our rehydration of our applications from the old armies to the new armies.
Next, we look at blue-green deployment automation. What is blue-green deployment? Most of you are familiar. We'll quickly review. This is courtesy of Martin Fowler. So we have a blue service running, and it was load balanced by this. And there is a brand new green service gets established, and you change the router. That's the basic. Basically, you establish the full capacity, and you change the router to go to the new service. So how do we accomplish this in this context? This is where we start. We have a blue service. This is a target group, in this case, application load balancer. We have 2 tasks running for this use case across 2 EC2 instances, let's say. So this is our starting point. Now, we have a green task. So we launched a new service, which is basically a newer version of the same service. It gets its own target group, own beta ELB, call it as green ELB or beta ELB, and application developer does all kinds of testing. This is still running, no interruption to this, nothing happens here, and the application developer does a beta testing for whatever number of days. So far, so good. Now, I want to switch the traffic. How do we do? So we run a Lambda. All of these are triggered by Lambda functions, the way we described before. So we detach this whole set of containers, the ECS service, from this target group. We detach the whole target group and attach it to the same load balancer with a higher priority. If you are familiar with the ALB, you would understand. If not, the priorities, you can have several target groups attached to a same application load balancer, and depending on which has the lowest number, that is the highest priority. So it gets load balanced. In this case, we attach, let's say the priority was 400, for example, for the blue service. We detect one number, say 399, and we attach this target group to this ALB, and what happens is this target group, the ALB basically starts routing to the listener routes to the green tasks, and the blue one slowly gets the in-flight transactions complete, but they are not drained, they no longer get the traffic anymore because we haven't stopped the containers yet. So at this time, all good. Now the developer has to make a call, operations personnel. Okay, there may be Splunk reports or other things which tells you that something is going wrong or you're good. Let's say you're on a happy path, you want to go ahead and move forward. So in this case, what we do is we delete the blue service, which basically that's the two-stage. It stops, drains, and deletes it. Then also we deleted the beta ALB also. You can hang on to that if you want to test more services, because you don't have to create one beta ALB for each service. Say if you want to roll back, so we will do just the opposite. You submit the same Lambda function with the parameter file with the action called rollback. We will just do the opposite of the original state. Basically, we remove the priority, and the blue services start getting traffic to the original task, and then we have a next action that will delete the green service, and you can start all over. So that's how blue-green deployment happens.
So canary deployment, right? And not every application follows the same release strategy in a large enterprise, right? On some applications, you want to incrementally release the new version of the app along with the older version and see how it is performing. And based on the performance that how your new version is working alongside the old version, you will take decisions. I have released 1% of my containers, the new version with the older version, and you would say everything is looking good, let's increment it. Let's go forward by like 10%, and let's wait and see for like 30 minutes to see how it works. And you would make such decisions. And at some point, you would say, hey, I don't need like I don't want to go forward, I want to roll back, something is not looking good. So you can roll backwards from going to like from 10% to 20%, you will go from 10% to 0%, so your older version works. So how do we support this type of canary release strategy with this automation tooling, right? So like we say, like we have, let's say like we say like 10% you want to release here, and then wait for some period of time, and you release 30%, and then you make it go all the way if everything is looking good. And all along, you have the same load balancer where your clients, the clients don't see any change of you releasing your new version of the app into the mix. So as an application developer, what do I have? I have like this is my deployment ID. I'm just giving it an ID, saying this is my deployment ID for my canary release deployment. And this is my cluster, ECS cluster, and I have my blue service, V1, and I have my green service, V2. And we have like a number of tasks, and this is the task definition. So this is where it gets interesting. I'm going to say here, I want to increment my canary release by 20%, and I want to wait for like 15 minutes. And if everything is looking good, then I want to go forward every 15 minutes. And while I increased like 20% of my canary, I want to roll back my original ones by 15%. So I don't want to run like 100% of blue and 100% of the newer version and 100% of the older version. And what is this action? This is deploy, right? So I prepare this property file, drop it in the S3 bucket, and it's going to trigger my Lambda function, which does this canary deployment. And this is the set of tools or that we use in our canary deployment. So let's go over how these things work. So again, as you can see, we use all AWS native services here. We use S3 bucket, we use Lambda function, we use SQS, and we use SNS topics for like sending notifications, and we use this our ECS cluster. As like we just reviewed, as an application owner, I am preparing my deployment file. I am telling what is my ECS cluster and what is my older service and what is my canary service, and I drop into the bucket, and my action is deploy. And this will trigger the Lambda function. And what does the Lambda function does? It goes to my ECS cluster, and at this point, I have two services. One is the older service, and the other one is the canary service. It's going to increase the number of containers in my canary service by 20%. And when all those canary service containers come up and they all get registered in the same load balancer, the same target group, when those are all done, then it also goes and decrement by 20% the older service. It does that, and then it drops a message into the SQS queue saying, I did this much. I incremented my newer version by 20%. I decremented my older by 20% and drops that message in the SQS queue. And it also puts that message in the S3 bucket where we maintain the state of this deployment, right? And once it does that, then it also sends a notification to the operations folks of what just happened. It incremented the canary version by 20%. That information also is published to this SNS topic. And we have another Lambda function, which is a polling function to this deployment queue. It goes there and looks, oh, I said like that time was like every 15 minutes. It polls and gets that information here. And based on that, it goes and again updates the service. So every 15 minutes, as long as there is no interruption, it goes and starts incrementally rolling out 20% of your canary version. And once those gets registered into the service target group, it goes and it decrements the older version by the same amount. It continues to do that until all of the canary version is 100% and the older version is off of the traffic here. Right? So this is the happy path what we just reviewed. And while this is happening, let's say like the first 20% is up and you are watching your logs and you are seeing some errors showing up in the logs and you want to stop this thing. So what do? Go back in the same properties file, and here instead of deploy, you put a, so what do you want to do? Like you want to suspend and see what's going on. That is one action you can do. Or we are panicking, oh, nope, this doesn't work. Let's roll back everything. Then if that's the decision, you can say like a rollback. So we have two options here. I'm going to say like suspend. So I'm going to drop a action called suspend, drop it into the bucket, then everything stops there. So you have the 20% running, and that can you are getting the traffic going through that, and you can watch logs and see. And then you figured, oh, this is nothing alarming. This is something that was expected. I didn't have to stop it. Then go back to the same file here, and here you say like resume. So drop it again, and it's going to pick it up from where it was left and roll forward with the same amount of increments until you get 100% of this one. And the other actions besides what we just saw, the like deploy, suspend, or like roll forward, in the sense you are doing like here, other than like 15 minutes, you say like you wait like for 3 hours for every 20 minutes, or for every 20%. And you did this first 20%, you watched for 3 hours, everything looked great. And it does increment by another 20% after 3 hours, and everything looks great. And you are confident this is not going to go wrong, and you say like roll forward, then it's not going to like 60, 80, and 100 in the 3 hours interval. Every 3 hours, it's just going to go all the way to 100%. That is one action. So that is roll forward. So depending upon what your action during the canary release, you have options like deploy, suspend, resume, rollback, and roll forward. All of that uses this tooling, automation tooling, to make your canary price work well. Right? So, and lastly, some of the lessons that we learned here, right? So go ahead, Satya, cover the some of the important lessons we learned.
Thank you. We haven't have slides, but a couple of things I want to cover is we have implemented high availability in multi-region using Route 53, standard configurations from AWS. We have similar tools, Jenkins are Lambda based. You say that deploy it in this region, deploy it in this region. This is my resiliency policy, your routing policy. You can say that 60/40 latency based routing or whatnot. And what is your CloudWatch alarm for monitoring your health and all that stuff. And we have implemented that. And we have implemented auto scaling policies for both containers and underlying EC2 instances depending on various policies. And also, you saw that the blue-green deployment launches double the number of tasks. What if you don't run out of capacity? The reservation alarms, if you run out of 80% of your capacity, it will launch more. And once you eventually get rid of those instances, the green ones and the blue ones, once you destroy them, your capacity will be restored back to what your alarms are configured to. So ECS has significantly simplified our container stack operations, leveraging ECS, the native tools along with ECS. The integration is so powerful. And with this automation tooling, we have deployed several production deployments in minutes. We can say that. So the development teams have to just focus on the Docker images, test them fine, and not to worry about the infrastructure stacks. One last point on that is, we have been certified by AWS as a well-architected framework. We have, if you have an enterprise contract with support with AWS, you can also do it for your company. AWS has reviewed our design, and we were offered, I think it's like something like 95% compatibility. There are a lot of security. You have to balance between cost, security, and high availability. You cannot have 100 in all of that. When you have high availability, you have redundancy that increases your cost. Then when you want to do security, there are some things you have to do. So some of those may reduce your points. That doesn't mean that you are not well architected, but it's a good indication of how your application is due. If you have a AWS technical account manager, you can work with him to get the AWS well architected certification.
Yeah. So lastly, right? So we were very excited to see in today's morning presentation where they announced that the support for container placement. This is something we dearly like to have. And other feature that we would love to have is the container level security groups. As soon as we got the IAM at the task level, the ECS task level, the container level, we took advantage of those features. And we are looking to have container level security groups. Otherwise, we have to apply the total sum of all security groups to all of the EC2 instances, and I cannot run services that I want to isolate in a single cluster. I don't want to share the security constructs, right? So that is something we would love to see. And balancing placements with scale in and scale out. So this is always a tricky one, how you scale out and scale in, and you'll have to have the right configuration. Otherwise, you are saying like CPU 80% scale out, but memory, if it is going down by like 50% scale in, and you will go between scale out and scale in very awkwardly. And other things like we like to see the rather than to have the step up or step down policies, like when you hit like 80% CPU, we say step up like 2 machines or add 2 machines, add 3 machines. We don't want to be in that step up, step down business. Rather, we would like to say, I want to maintain a target rate of like 60% CPU. You, Amazon, behind the scenes, you take care of how many machines you want to add or how many machines you want to scale down, but give us the target rate that we want to specify, and not the number of step up or step down instances. So those are some of the things that we would like to see as the ECS product grows, and we are very thankful for our partnership with Amazon ECS product team and the IAM for like feature and other features. We had a preview, and the application load balancer, we had a preview, and Satya and I published a engineering blog in Amazon ECS website talking about all the details and different configurations and the different features of that one. So please check that one out when you get a chance. So that's about it for today's presentation, and thank you for your time.